In this problem, we're gonna study the variations and the concavity of some function defined by some integral. What we need here is we need to know the fundamental theorem of calculus and the properties of the derivatives, and also the properties of the second derivatives of a function. Okay, and also we need to be able to see or to study the function when we have the bounds not finite. Here x can be any. The good thing is that x is positive in this case. So this means that t is between 0 and x. Okay? And one key idea here to start working this problem is, what about this function here? Is it continuous? Where is it defined in terms of x? The good news is that this function is always positive in this case, and it's continuous and defined everywhere on R. But since we are just working on 0x, it's defined and continuous on this interval. Therefore, using the fundamental theorem of calculus, we can find the derivative. Okay, clearly f prime of x is just our function, let's call it g, evaluated at x. This gives us that the derivative is just e to the power x over 1 plus e to 2x. Since we want to study the variations on this interval 0 plus infinity, because our x is positive, it can be any. So here we see that this one is bigger than 0. Okay, in fact, it's strictly bigger than 0. And this means that f is increasing. So our function f is increasing because the derivative is positive. Therefore, the function f is increasing. The question that we need to ask, is it increasing in this way or in this way? So that means we need to study the concavity of the function. To do so, we have to determine the second derivative in this case. So this gives us that using the product rule. So this one is going to give us e to x times 1 plus e to 2x minus 2e2x times ex over 1 plus e2x squared. Let's simplify this one. We're going to get e to x plus e3x minus 2e3x over 1 plus e2x squared. This gives us e2x minus e3x over 1 plus e to the power 2x squared. Remember that we are working only on x for x positives, on the positive values. Okay, so we see that the sign of this second derivative is mainly is determined by this sign of this function e to the power x minus e3x, because this is always positive. Okay, without studying this one, we can do it graphically. Since we are working in the positive values, we can study this one only on the positive value. So both of them, they take 1 when x is 0. Okay, so this is the exponential, but the exponential 3x is increasing faster. So therefore, when we subtract this one from this one, we get a negative value. This is a negative value. That means the function f of x is less than 0 for all x positive. That means it's concave down. So it's in this behaves like in this manner. Okay. In fact, in this case, we can even compute the function f. Okay, we can use a change of variable here let e to the power t be y. Okay, in this case, when t is 0, we're gonna have 1. So when t is 0, y is gonna be 1. When t is x, y is gonna be e to the power x. And et is gonna be y, and here 1 over e to t is e to t squared. It's gonna give us y squared. And dt is et dt dy. Therefore dt is dy over y, dy over y. And therefore we have our function is being 1, the integral between 1 and e to the x of 1 over 1 plus y squared dy. And we know this one here. We know a primitive of this one. It's the arctangent of y between 1 and e to the power x. This gives us the arctangent of e to x minus the arctangent of 1, which is pi over 4. Therefore, my function, okay, this is very simple, becomes the arctangent of e to the power x minus pi over 4. Okay? And I can draw it, I can graph it. Okay? And I can clearly we can now deduce all these values that we need. Okay? So it's like shifting. The exponential is gonna slow down the arctangent, but it's not gonna be anything. It's just gonna be something like this. The value, the limit, so the exponential plus infinity and pi over 2 minus pi over 4 is gonna be pi over 4. So this is gonna be the value. So it's gonna look something like this. So this is our function. And clearly from here, we're gonna see that when we integrate, we're gonna obtain more values. That's why the function is increasing. Okay? So using calculus, we have proved that this one is positive and it's increasing and it's concave down. Okay? Anyway, you see any mistakes, or we don't edit these videos. If you see any mistakes or any errors, please let us know. And thank you very much for all your help.